Hey everyone, welcome to today's explainer. I want you to think back for a second to when you were a kid, playing around with those interlocking plastic building blocks. With just a few simple pieces, you could build a house, a car, or even a spaceship. Well, nature has its very own ultimate set of building blocks, and we call them hydrocarbons. In the world of chemistry, carbon is basically our master architect, and today we're going to learn exactly how it builds the physical world around us.
Okay, let's dive right into this. Before we get completely bogged down in the complex chemistry, let's ground this lesson in your everyday reality. Think about the LPG gas you use to cook dinner, the petrol you pump into your car, or the polythene plastic making up your water bottles. These aren't entirely different unrelated substances. No way. They are literally all just different arrangements of the exact same carbon and hydrogen toy bricks. It's absolutely incredible to think that the difference between an invisible gas that cooks your food and a solid piece of plastic is simply how these carbon atoms are snapped together. So, here is our lesson plan for today. First, we'll officially meet the hydrocarbons. 2, we'll look at alkanes, our simple carbon chains. 3, we're going to explore reactive bonds with alkanes and alkynes. 4, we'll tackle benzene rings. And finally, step 5, directing the blueprint. All right, part 1, meet the hydrocarbons. We are climbing the complexity ladder.
Think of this hydrocarbon classification table kind of like a video game, where we're leveling up in complexity. It's fascinating to see that at the very top we have alkanes. These are saturated, which just means every single carbon block has single bonds, holding on to as many hydrogens as it possibly can. They are super stable and pretty inert. But as we move down the ladder to alkenes and alkynes, we introduce double and triple bonds. These are unsaturated, and that completely changes how they react. Suddenly, they're super eager to connect with new atoms. And finally, at the bottom, we hit the arenes, like benzene, which use these really complex ring structures. Let's see how all of this builds from the ground up.
Moving right along to part 2, alkanes, our simple carbon chains. This is the sturdy foundation of our chemistry building blocks. And this brilliantly illustrates what happens when we map a single carbon block in 3D space. We get methane. It's one carbon atom right in the center, firmly bonded to 4 hydrogens. Notice that highly specific angle there? It's exactly 109.5 degrees. That gives us a tetrahedral shape. You see, it's not just a flat drawing on a page, it's a robust, highly specific architectural structure. These single, extremely sturdy bonds are exactly why simple alkanes, like the methane in your home's water heater or the propane in your backyard grill, make such excellent, reliable fuels. They safely store up all that energy until we provide a spark.
But hey, these blocks aren't just frozen in place. When you snap 2 carbons together to make ethane, the 2 ends can actually spin and rotate around that single bond, almost like a propeller. And as the molecule spins, its potential energy changes. The atoms naturally want to settle into what we call the staggered conformation. Now, why is that? Simply put, because the hydrogen atoms want their personal space. Being staggered keeps their electron clouds as far apart from each other as physically possible. This minimizes repulsion and makes the whole molecule incredibly stable.
So, how do we actually do chemistry with these stubborn, sturdy little bricks? Well, we use something called substitution. It works exactly like a step-by-step instruction manual. If we mix methane and chlorine gas together, absolutely nothing happens in the dark. But if we introduce diffused sunlight, that energy breaks the chlorine apart. Suddenly, one of our hydrogen blocks pops right off the methane, and a chlorine block snaps perfectly into its place. We can keep exposing it to light, substituting more and more hydrogens, all the way until we've completely swapped them out to make carbon tetrachloride.
All right, let's level up. Part 3, reactive bonds, focusing on alkenes and alkynes. It's all about adding new connections. Let's take a really close look at a double bond. When carbons share 2 pairs of electrons, something totally fascinating happens. They form this flat, planar shape, but notice those orange zones hovering above and below the central connection? That is the pi cloud. This pi cloud holds onto its electrons very loosely. Because those electrons are just hovering out there, exposed and vulnerable, it's amazing to see how alkenes are incredibly eager to snap that double bond apart just to grab onto new atoms. This process is called addition, and it's exactly why alkenes are the perfect starting materials for making vast, endless chains of plastics.
And if we add a triple bond, we get alkynes. The structural geometry completely changes once again, becoming perfectly linear, just a straight 180-degree line. But there's a wild side effect on the acidity spectrum. You see, a triple bond pulls the shared electrons so incredibly tight toward the carbon nuclei that the hydrogen atoms on the very ends are practically left hanging. They become highly acidic. In fact, if you react an alkyne with sodium metal, that little terminal hydrogen block will just pop right off and release pure hydrogen gas. Which brings us to part 4, benzene and aromatic rings. Welcome to the boss level of chemistry. Benzene has an absolutely brilliant origin story. Back in 1825, early scientist Michael Faraday first isolated this mysterious substance, but nobody could figure out its shape. It had the formula C6H6, which meant it should be highly reactive, but it wasn't. Then, in 1865, a chemist named Auguste Kekule famously had a daydream about a snake eating its own tail. He woke up and realized benzene wasn't a straight chain at all. It was a closed ring with alternating double and single bonds. Today, modern resonance theory reveals an even deeper truth about that shape. Which brings us to the ultimate question for you guys, our reactivity paradox. I just told you a few slides ago that double bonds have exposed pi clouds that easily snap apart to add new atoms. So, if benzene is a ring containing 3 double bonds, why does it fiercely resist addition reactions? Take a second to really think about that. Why does this specific toy brick break the rules we literally just learned?
So, the crucial point is that the resolution to this paradox comes down to Huckel's rule and complete delocalization. Actually, benzene doesn't have 3 isolated double bonds at all. Instead, the electrons from those bonds smear out and are shared equally by all 6 carbons. This creates a continuous, donut-shaped cloud of energy above and below the ring, providing unprecedented thermodynamic stability. To protect that incredibly stable shield, benzene flat-out refuses to undergo addition reactions. Instead, kind of like the alkanes we saw earlier, it relies on substitution. It's happy to swap out a hydrogen for a new group, but it is going to protect that core ring at all costs.
Finally, part 5, directing the chemical blueprint. We're talking about molecular traffic cops.
Now, we can't just snap pieces onto our ring randomly. We need molecular traffic cops to direct the flow. When we substitute the first hydrogen on a benzene ring with a brand new chemical group, that group gets to dictate exactly where the next piece is allowed to go. We essentially have 2 types of COBs. First, activating groups push extra electrons into the ring. This creates highly negative target zones at specific spots called the ortho and para positions, practically waving in the incoming chemicals. On the flip side, deactivating groups withdraw electrons, starving the ring of density and leaving only the meta position open for business. By choosing our very first attachment, we completely control the blueprint of the final molecule.
And to bring this entire lesson full circle, how do we actually get from our simple linear alkyne chains up to our complex aromatic rings? Cyclic polymerization. By taking ethine gas, just a simple 2-carbon block with a triple bond, and running it through a red-hot iron tube at nearly 900 degrees Kelvin, we literally force 3 of those small molecules to fuse together. The triple bonds break, rearrange, and snap into the shape of a perfect, highly stable benzene ring. We just took simple cooking gas building blocks and synthesized the foundation of complex pharmacology.
As we wrap up today's explainer, I want to leave you with this final, provocative thought. Nature has given us a finite set of chemical building blocks, but infinite ways to assemble them. If merely rearranging a few simple carbon and hydrogen atoms dictates whether we're holding a plastic bottle, fueling a rocket, or curing a disease, what undiscovered structures are still out there in the vast architecture of chemistry, just waiting for you to build them? Thank you so much for joining me on this climb up the complexity ladder, and I'll see you all in the next explainer.